keep it sadar, like on so skiddy, 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 skiddy. So skiddy, 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 skiddy. Aduh banyak lekong, mari kita kesontong. Cuma boleh mau gegen lekong, lekong, betong, lekong, betong, 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 lekong, lekong, betong, lekong, betong, 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 lekong, betong, 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 lekong, betong. Jadi melong karena pe banyak lekong, jalur-jalur baku jalur, eke so mulai mebong. Lekong so skiddy, 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 skiddy.
integrity, and respect. This is STAR Training Center, sustaining teacher leadership and academic vitality through research. Let us remember that we are in the loving presence of our Lord. Lord, we offer you our webinar today. Make this a safe and healthy place for learning. Help us to be engaged and challenged as we go on through our topic today. Support us so that all our learning activities be accomplished for your greater glory. Above all, help us to have a good heart so we can be an instrument to do good things. We ask all these in your glorious name. Amen. Before we begin this webinar, here are some important house rules that we shall observe during the entire duration of our webinar. First, stay focused and don't multitask. Also, please close all apps that could influence connection speed. Second, take notes. Take down the key ideas you will hear. Third, ask questions concisely. You may type your questions in the chat box. Our learning facilitator will try to address all your questions during the question and answer portion. Lastly, respect the learning facilitator and other participants. Be respectful. Keep your contributions helpful and considerate of the learning facilitator and other participants. Thank you.
Good morning, everyone. Kamusta po tayo? I hope everyone is safe and well at our respective homes. Anyway, we are now on our fifth live session, and our topic for today is about factor analysis. So without further ado, may I now call on screen our resource speaker, Dr. Carlo P. Magno. Good morning po,
Okay.
Doctor.
Good morning. Good morning, everybody. So this is another Saturday of analyzing your data. And for today, we're going to have a session on two approaches on how you actually conduct factor analyses. So we'll talk about and demonstrate how exploratory and confirmatory factor analyses are conducted. Okay, let me share my screen now. Okay, you can see my slide now.
Yes po, Doctor.
All right, just increase the volume. All right, so we're going to talk about conducting exploratory and confirmatory factor analyses. So this is the outline of what we're going to talk about for this morning session. Okay, we'll start by looking at multiple variables. How do we deal with variables that are composed of several factors? And this is very much connected with the session that we had on validity last week, because our major concern here is to identify whether a particular variable that is being measured by a tool is composed of several dimensions or factors. If we know that a particular variable is composed of several dimensions or factors, then we would know specifically how to do some proving whether this variable is actually supported by our data. And then we'll talk about the two different approaches on how to analyze variables with multiple factors, such as exploratory factor analysis. More specifically, we're going to talk about the principal components analysis, and we'll talk about confirmatory factor analysis, making use of a structural equations modeling approach. And then we'll focus more on testing the model with multiple variables. Okay, and we'll talk about confirmatory factor analysis. Now, if we still have time, we'll talk about how to report results of your confirmatory factor analysis. Okay, So when you say that a variable is composed of several factors, we now say that the variable is multivariate, meaning to say the variable is composed of more than one factor or multivariate. And usually the analyses or the statistical techniques that we use to deal with variables with more than one dimension are what we call as multivariate analyses. So the requirement for a multivariate analysis is that your measure or your tool is, of course, obtaining quantitative data. And this quantitative data for your variable are classified according to a set of factors or subfactors, which we call as well as subscales, subtests, or domains or subconstructs. Now, when we talk about multivariate analyses, we're concerned about two things. The first one, okay, how do we actually regroup the factors of our data, especially if our data is composed of several variables? How do we now regroup them or group them together, especially if they share a common characteristic? The second is, how do we actually now see the connection among all of these factors as guided by a particular theory? Now, take note that our analysis and interpretation, according to MESIC, needs to make sense in terms of its theoretical rationale. So in the end, we're actually conducting all of these analyses of grouping and regrouping a large set of variables, because in the end, we want to make sense with our data. And this is part of looking at the theory that we are actually building or supporting. Okay, let's start with this initial concept. So when you talk about variables such as height, thirst, and self-esteem, height can range in a continuum from shorter to taller. Thirst can range from less thirsty or more thirsty. Self-esteem, according to previous framework, are ranging from less to more of one's self-esteem. So what is common among these variables is that they are measuring a single continuum from more to less or less to more. However, if you look at other variables such as achievement, you can actually break apart achievement. So when you talk about achievement, it doesn't refer to a single construct. One can achieve in terms of one's verbal ability. One can achieve in terms of quantitative, such as mathematics. Therefore, some variables, usually like achievement, okay, cannot be measured in a single continuum as compared to these variables that I have previously shown. So therefore, we measure them across more than one component, such as mathematical achievement or English achievement or language achievement. So you will see that this is now composed in the illustration, composed of two dimensions. Therefore, achievement is an example of a multi-dimensional variable, and your variables such as height, thirst, and self-esteem are examples of unidimensional variables because they only measure a single construct. So this is the definition of a unidimensional scale. So you're aimed here at selecting a set of data items that empirically demonstrate or correspond to a single social psychological dimension. And usually the analyses that we use for unidimensional scales are the Thurstone or equal appearing interval scaling, the Likert or summative scaling, or the Guttman or commutative scaling. But we're not going to focus on the unidimensional scaling for this session, but rather we focus on how we analyze constructs in a multidimensional scaling. So when you say multidimensional scaling, there is more than a single dimension that underlies a set of observations. So meaning to say that aside from measuring the degree of the object, we also classify the variables into two or more properties. And these classifications are what we call as latent constructs or factors or subscales or manifest variables or domains or subvariables. So when we use these names, we're all referring to them as factors. And when we say latent construct, we're now referring to the overall variable that we are measuring. And when we say that the variable is latent, it means to say that it is composed of factors. Let's move on. So what analysis do we use for multidimensional scaling? There are several analyses that we can actually use for variables that are multidimensional depending on our purpose. If our purpose is to explore or determine the underlying factors of a latent variable, then we use the following analyses. You can use a principal components analysis, a multidimensional scaling, a joining tree clustering, or k-means clustering. I need an entire term on an advanced psychometric theory course in order to explain all of this, but for this particular session, we'll just demonstrate principal components analyses. Okay, and the other approach is what we call as confirmatory factor analysis, where we use a statistical technique called structural equations modeling. And we'll demonstrate more on confirmatory factor analysis. Okay, so let's just practice a little bit. Can you give me examples of unidimensional and multidimensional variables? Let's start first with unidimensional variables. Let me stop sharing my screen now. Okay, Loida. Hello, Loida. Can you turn on your microphone, Loida? Hello, Loida. Yes, Loida. Can you give me examples of unidimensional variables? Hello, Loida. I can't hear you. I think Loida is having internet problems. Okay, let's try Lorna. Miss Lorna. Hello, Miss Lorna. Can you unmute? Hello, Miss Lorna. Okay, Lorna does not like to unmute. Alfredo Ofresio. Sir Alfredo? Sir Alfredo? Okay, anyone who likes to volunteer? Okay, anyone who likes to volunteer? You are all putting your answers in the chat box. Okay, so happiness. Just take note that happiness, making use of the framework of Seligman, is now multidimensional. Okay, example of a happiness framework, such as well-being by Seligman, is composed of the PERMA model, PERMEA, 5 factors. Okay, so happiness is multidimensional. Yes, this is from the Secretariat. Okay, IQ. IQ is multidimensional. Height of people, weight of cars are unidimensional. Yes, correct, Sir Sunny. Okay. Liquid, volume are unidimensional. Weight are unidimensional because these are already the examples that I have provided. Range of motion is unidimensional. Ms. Odette, you're correct. Activities of daily living. Caring, okay? There's a framework on caring, and caring is composed of 2 factors in a framework by Gordon. Okay, so you have empathy and compassion. So caring, or capacity to care, that's the name of the variable, is multidimensional. Mobility, I'm not sure what framework on mobility is. Okay, speed is multidimensional. Satisfaction. Satisfaction on what? You have to be specific, Gabriel. Jerome, stress. Stress is multidimensional. Anxiety, yes, is multidimensional. All right, so how do you know? The next question now is, how will you know? Okay, Gracita, can you unmute your microphone? Miss Gracita Bernal. Miss Gracita. Hello, Miss Gracita Bernal. Hello? Elaine Hubo. Elaine?
Yes,
Okay.
sir.
Ayan, hay salamat. May nag-on ng microphone. Okay. Okay, so Miss Elaine, how will you know if a variable is unidimensional or multidimensional?
For me, sir, based on my own opinion, we could know that a certain variable is multidimensional if it is somewhat like not measurable in the terms of quantity, but more or less that's more on a qualitative aspect.
Okay, Elaine, let me do some correctives here. Okay, Elaine,
Yes, sir.
all variables are measurable.
Yeah. Okay.
So if it is not measurable, then it is not a variable.
Okay.
Okay.
Difficult to measure, siguro, sir.
All variables can be measured. Therefore, there is no easy to measure. There is no such
Okay.
thing such as difficult or easy to measure.
Okay, sir.
So as long as it is a variable, it is measurable, and there's a way to measure it.
To measure. Okay. Thank
Let
you,
me give
sir.
you a clue now, Elaine. Based on my
Yes, sir.
original question, how will you know if a variable is unidimensional or multidimensional? Let's say, for example, well-being. A while ago, I mentioned that there is an existing model of well-being by Seligman. What is your profession? Are you in psychology, Elaine? No.
No, sir.
Anyway, now, according to Seligman, that well-being or happiness is composed of positive emotions, engagement, relationships, motivation, PERMA. And A, I forgot the letter A. Okay. Now, I knew that well-being is multidimensional because I've read Seligman's
Yes, sir.
work. Okay, so that's already a clue. How will you
Okay.
know if a variable is unidimensional or multidimensional?
Maybe there are another sub variables
How will you
under.
know? How will you know, and who will tell you if there are subfactors? Are you going to guess on your own?
No, sir.
No. Who will tell you if the variable is unidimensional or multidimensional?
I think it must be based on a valid individual or valid literature.
Very good. Okay? In order for us to determine whether a variable is multidimensional or unidimensional, we need literature review.
Okay.
It is not us who will be the one to say whether it is multidimensional or unidimensional. You need to read literature review. More specifically, from the literature review, you need the conceptual or
Framework. Theoretical
framework. It's the conceptual or theoretical framework from the literature review that will tell us whether it is unidimensional or multidimensional. So it is not us, it is not you who will guess. Okay? You need to read first, okay, a journal article, and the journal article will tell you whether that variable is uni or multi-dimensional. So it is not you, Elaine, who will guess. Okay? Another question, Elaine. Ay, asa na siya? Hello? Where is she? The one that I'm talking to. Hello, Elaine? What happened? Hello, Elaine? Bakit hindi na maka-unmute? For the host, kindly please allow the participants to unmute.
Good morning, Doctor. Allowed naman po sila.
Elaine, you're allowed to unmute.
Okay na po,
Ayun.
sir. Kanina po kasi not allowing pa po.
Okay, Elaine.
Yes,
So
sir.
therefore, so what do you need to do first? So when you select a particular variable, meaning to say, what do you need to do first?
You need to have a literature review of a
And what do you
certain
look? Yes.
variables that you are.
And what will you look for in the literature review?
On a conceptual or theoretical framework that will be the basis of a certain variable, sir.
Yes, you need to look for the theoretical or a conceptual framework, and that's the one that will define whether it is unidimensional or
Unidimensional, sir.
multidimensional. So pwede bang can I invent my own variable and say it is multidimensional, Elaine?
No, sir.
No. What if I have a particular variable in mind and there is no conceptual or theoretical framework for it? Elaine, what will I do?
Maybe, sir, you could, maybe you could, if ever you have a certain variable that's no literature review that will be the basis for your variable, I guess. If I'm it is either you change or it may be you need to have, if you want to focus on that on your certain variable nga imo na for you may have you make your own.
How do I
guess,
make my own?
You make your own framework, and that will be again the basis of proving.
How will I make my own framework?
I don't know, sir. Sorry.
Okay, yeah, you can do several approaches. You can do qualitative first. Okay, you can do ground theory and to establish the variable, okay, that you have after you have collected and are able to identify a good definition and good manifestation for your variable through your qualitative analyses. Then you can create a set of indicators and create a tool, and then you proceed with this analysis.
Okay. Sige, thank you, sir.
However, it's very, very difficult to create a new variable. You need to have a very, very good basis. And even if you create your own variable, it starts with a previous or connected conceptual or theoretical framework as well.
Yes, sir. You will find difficulty, sir.
Yes, that's why I like your first suggestion. If there's no theoretical or conceptual framework, change your that's actually a very wise a very wise suggestion, especially if you are doing a particular study or any you're an undergraduate or your master's level. Framework. All right, we're discussing this one first because these concepts are prelude to conducting factor analyses. Take note that factor analysis is just your statistical analysis. It should be grounded on a very, very good framework to begin with. All right,
yes, sir.
Thank you, Elaine.
Yes, sir. Thank you.
So, host, you can unmute everybody again. So you can see my slide now. Host, can you see my slide? Oh, the host is missing.
Yes po, Doctor. Sorry.
Okay. Now, here are examples of variables that are composed of more than one dimension. multidimensional. Example would be gender identity. This was actually derived by Sandra Bem in the 1980s. Okay, and then she made an instrument called the Bem sex role inventory. And she said that gender identity runs in a continuum from masculinity to femininity. So it means that certain individuals may possess masculine to feminine characteristics. And Sandra Bem conducted factor analysis. And then Bandura made the regression scale. Okay, and he used factor analysis as well, okay, in order to derive his two factors of aggression, which is physical aggression and verbal aggression. And then in 1996, Fisk and Glick established the variable called sexism, and they conducted factor analyses and confirmatory factor analyses, and they were able to derive two factors, which is benevolent sexism and hostile sexism. Even your other theories like the two-factor theory of intelligence by Spearman, he said that intelligence is composed of two factors, the G factor and S factor, because they conducted factor analysis. They didn't invent outrightly, oh, intelligence is composed of a G factor and S factor. Okay, no, they did factor analysis in order to derive how many factors are actually going to be composed for their variable. Also, and then later on, the student of Spearman, like Cattell, made his own intelligence scale, and he conducted factor analysis. That's why he was able to arrive at factors such as crystallized and fluid intelligence. Also, Myers and Briggs, okay, studied about temperament. They made a measure of temperament and arrived at subscales on extroversion, introversion, sensing, intuiting, thinking and feeling, judging, and perceiving. So meaning to say, all of these previous framework, all of these previous models, they didn't just invent their variables. They conducted factor analysis. Okay, so you notice that their approach here is that they have a major variable like intelligence, and they're breaking apart intelligence into specific factors, okay, like crystallized and fluid. And this is the function of factor analysis. You're actually decomposing a latent variable into a more observable and measurable variable. And the first approach that we're going to talk about is exploratory factor analysis. Okay, give me 1 minute for a restroom break. Okay, I'm back. Okay, one more story. Oops. Okay, one more story before we go on into the analyses. All right, you see other intelligence variables such as that of Cattell, Binet, Spearman are actually the more acceptable and valid variables of intelligence. Why? Because they conducted factor analysis to arrive at their varieties of intelligence factors. Now, take the case of your favorite author, okay? And he made his concept on intelligences, which you recall as multiple intelligences. All right? Elaine, as a host, can you unmute again the
Hello,
participants?
sir.
Okay. Yes, Elaine. Of course, have you heard about your favorite author, Howard
Yeah.
Gardner?
Yes, sir.
Okay. And Howard Gardner is very popular, right, Elaine?
Yes, sir.
However, you know, Elaine, in the research literature, Howard Gardner is not popular. You know why?
Really, sir?
Yes, he's not popular, meaning to say, researchers who conducted factor analyses are criticizing his verbal, what else? Mathematical intelligence, logical,
Not,
ano yung mga ano niya?
yes, entra and
Interpersonal,
enter. Yeah.
intrapersonal, yes. The numerica, the naturalistic, the existential, he
Uh-huh.
added. Okay, he's being criticized since he started his multiple intelligences. You know why? Elaine, you have a clue,
Yes, sir.
Elaine? Ano?
I don't know, sir.
He arrived with the verbal intelligence, the logical mathematical, the
Yeah.
interpersonal, the intrapersonal, okay? The visual spatial, the kinesthetic, because he just made them. He did not derive them through factor analysis.
So it's just
Mm,
only his own
thinking.
idea or mind based on his
Yes.
own concepts. Okay.
Yes. That's why there were several issues on multiple intelligences. Okay? Now,
Yes,
that's
sir.
why, however, it is popularized because his information is accessible to everybody. He made that book. And that book, you can just buy that in National Bookstore and read about his book. But you will, there's a story there how he arrived with his multiple intelligences, but they're not derived mathematically through factor analysis. That's why he's not very popular in research literature. However, the ones made by Cattell, okay, Myers and Briggs, Spearman, and Binet are the more valid measures of intelligences because these factors were derived making use of factor analysis. Okay? So everybody, you get the point now. You don't just simply invent something that you want, such as factors. You conduct factor analysis to prove your idea. Okay. So here are the analyses. Okay. So the first one is exploratory factor analysis. We'll just breeze through a bit on exploratory factor analysis so that we can concentrate more on confirmatory. So you're using this particular approach, EFA for short, exploratory factor analysis, because you wanted to reduce the number of variables. Example, you have a measure and it is composed of 100 items. So each of those items are considered to be as variables. Therefore, you wanted to reduce them. How do we put together some of these items that are similar and put them in a category? And that is the reduction that we are talking about. At the same time, we are detecting the structure in the relationship between the variables. When we are detecting the structure of the variables, we are now determining how many factors can we have out of those 100 items in a scale or in a measure. If we start to classify now these individual variables, let's say these 100 variables will fall under 5 factors, so we can have about 20 for each, say for example. It means to say that we have now reduced all 100 items, okay, into 5 factors. And the scale or the measure is now composed of 5 factors. And that's how we actually detect the structure. And later on, you can name the factor after you have looked at the contents of each of the items. So we define a factor in an EFA approach as a set of highly intercorrelated variables. Because in the analyses that we conduct, especially making use of the principal components analyses, these items or variables are actually put together if they are highly correlated with each other. Mathematically, that's what happens in the analyses. Okay, and we'll focus on the principal components analyses. In the principal components analysis, there are three important things that we need to look at in the results. First, okay, we look at the factor loadings of each of the items. The factor loadings of each of the items will tell us where does that item belong to? What factor does that item belong to? We look at the eigenvalue. The eigenvalue guides us on how many factors can we actually have for the entire measure or tool. We'll talk about factor rotation in order to maximize the distribution of items across the factors that you're able to extract. You use and look at the factor rotation. We'll not talk about principal factor analysis anymore. We'll just focus on principal components analyses. Okay, so the idea here in a principal components analysis is that we're combining variables or items in a measure that are highly correlated with each other. And if these items and measures are highly correlated with each other, it means to say that we can now form a factor out of it. Therefore, each item is indicative of what we call a factor loading. So the factor loading are actually correlations between the factors and the variables. And this is our cutoff point to say whether that particular item will load highly on a particular factor. Okay, so if you get at least about a factor loading of 0.30, it means to say that that item or variable is contributing meaningfully to that factor. And if you get a factor loading of about 0.40, it means to say that it's contributing very high to that factor. Okay, here is an example of what comes out in a principal components analysis when you try to identify the factor loadings of each factor. So this is a measure of self-disclosure that we did a couple of years. Okay, so there are 10 items that I'm only showing you. The entire scale is about 60 items. Okay, and then we conducted we administered the scale, okay, to about 328, and then we conducted factor analysis because our aim here and we have out of our 60 items. Okay, you will notice here that there are values after each of the item. Under F2, 0.2 under F3, 0.11 under F4, 0.1 under F5. In the analysis, what principal components analysis is going to do is that it will try to load item number one across different set of factors. However, that item will load highly only on a specific set of factors. Now, remember our cutoff, at least 0.3 or 0.4. Let's say I decided that I want to have a factor loading. I want my item to be highly contributing to that factor. So item number one now will be loaded under factor 1, and I will not put it under factor 2, 3, 4, and 5 because they're not highly contributing to these factors. In the same way, if you look at item number 7 is loaded highly under factor 1. So it means to say now that item number 1, I share views about God, and item number 7, I don't make my intentions a secret, are together under factor 1. Okay? And then item 4, okay? Item 6, item 9, and item 10 are all together under factor 2. So that's how I classify now my items according to factors by looking at those at their factor loadings. Okay, now, however, look at the case of item number 7. If my cutoff is 0.4, how come that item number 7 is highly loaded under factor 1, and it's also highly loaded, highly contributing to factor 4? Where will I put now my item number 7? Will it be under factor 1 or under factor 4? If such cases happen, this is now telling us that item number 7 is is a bad item. Why is item number 7 a bad item? Because item number 7 content is shared by 2 factors. We cannot distinguish what item number 7 is really measuring. Is it measuring factor 1 or is it measuring factor 4? Therefore, what we usually do is that we take out item number 7. We take out those items that are highly loading into more than one factor because we want each of the items to exclusively contribute to one factor only. So this is the idea of a principal components analysis. Next, the eigenvalues. Okay, so the eigenvalues tells us how many factors can we form in a tool. Remember my example a while ago. If I have 100 items, you want to uncover or detect the structure by determining how many factors can we form out of those 100 items. And it's the eigenvalue that will give us that information. What eigenvalue does is that it computes for the variances successively for every factor that it extracts. Usually, when you look at and assess eigenvalues, the first factor will have the most number of items under that one, because usually the first step will load most of the factors because they're all highly correlated with each other, and the remaining variables that are not highly correlated will be extracted on the succeeding factors. That's why usually it's the first one. Now, here is an example of a result that comes out on eigenvalues. Okay, I have here 30 item measure on responsibility for learning, and I conducted principal components analysis. And you will notice the eigenvalue that factor 1, if I will have one factor for my scale on responsibility for learning, it explains about 30.86% of the total variance of my items. If I have 2 factors, it explains about 5.86% total variance. If I have 3, it explains about 5.12. So I'm now looking at the total variance. Okay. Now look at the eigenvalue. Okay. The more factors it extracts, the lesser the eigenvalue becomes, because you're now splitting out your items to other factors. So how does this information, how does the eigenvalue or the second column labeled as eigenvalue tells us how many factors? Okay. One way, or the most traditional way, is to have a 1.0 cutoff. If the eigenvalue is 1.0 and above, okay, meaning to say you can have that extraction as the number of your factors. If you will look at our values here in the second column, eigenvalue, so the last value with 1.0 and above, okay, is 1.01. And that is the 6th extraction. So it means to say that you can form 6 factors out of the 30 items of my measure. Okay, because the eigenvalue of the 6th factor is 1.01. I will not have a 7th factor because the 7th factor only explains about 3.18% of variance, which is an eigenvalue of 0.96. And it is less than 1. So that's one traditional rule on evaluating your eigenvalues. Now, however, the problem now here is that if I will have about 6 factors out of my 30 items, so it means to say that I will have about expected about 5 items for every factor. And still, it's not a good way to explain now my entire scale, because I have not really reduced my data. I still have several variables under that one. It also happens sometimes that if you have 100 items, eigenvalue will tell you that you can form about 12 factors or 15 factors, and it doesn't explain well now your scale. And sometimes you're left out with having only one or two items under a specific factor, especially on the last one. That's why there are other ways of evaluating your eigenvalue. You can actually make use of the Kaiser Criterion. And the Kaiser Criterion is the one that we have just talked about. Look at the cutoff of 1.0 and above. The other one is what you call as the scree test. So in a scree test, you look at the sudden drop or the plateau in your eigenvalues. So you need to graph your eigenvalues into a scree plot like this, and then look at where there is a sudden drop. In this particular case, you will see that there's a sudden drop. So the first point here is your factor 1. The second point here is your factor 2. The third is factor 3, factor 4. Now, look at the point between factor 4 and factor 5. There is now a sudden drop. So meaning to say, if there's a sudden drop in your eigenvalues in your scree plot, that's where you stop counting on the number of your factors. So you can have 1, 2, 3, 4. So meaning to say, you can decide to have 4 factors making use of a scree test for your scale. Okay, so I'll show you how principal components analysis is conducted making use of a software called Statistica. Okay, so I will open. Can you see my screen? Host, can you see my screen? Okay. Where is our host now? He is not speaking.
Nakikita po, sir.
Okay, nakikita. Okay, host, you can see my screen and I'm opening Statistica.
Yes po, Doc.
Okay.
Yes po, Doc.
All right, all right. So I have opened now my Statistica. So first step is that I will open my data and I have placed my data in Excel. So I will open my Excel inside Statistica. I will import my Excel file inside, and that's possible. Okay, so first I'll have to search where I placed my data. Okay, I'll just open it. It's inside. Another S. Okay. PQRS. Here. Okay. Now you will notice that I have already opened my folder and nothing is coming out. Okay, because it's now searching for a Statistica file. So in order to do that, you just click the arrow down here and then click on all files, and then all files inside that folder will come out. So my data is here, lower version, okay, and then I'll open my data. This dialog box appears. It says here import all variables or import selected sheet. Let's say I only want to import a selected sheet, and that's the last sheet, responsibility data, because the scale is measuring responsibility for learning. Okay, then another dialog box comes out. You need to check get variable names in the first column because I have placed labels in my first row, and that's not included in the analyses. That's why I have to get variable names on first row so that it will not be included in the analyses, and you can see the labels here. Oh, I have not checked. Okay, let me do it again. Sorry. Open all files, lower version, open, select sheet, select the sheet that you want to analyze, and then put a check on get variable names from the first row. Okay, and then click OK. Now you will notice that the labels are now placed on your tab, and what you only have on the worksheet are the specific values. So I just placed here some tags like case number, the name of the participant, the school where they came from, the year, their CGPA, their gender, if they're under scholarship or not, and whether they experienced failure. And my items are labeled as D1, D2, D3, D4 until, let me just put my screen down. Okay, until item number 30, empty 30. Okay, so in order to do the menu in Zoom is covering my screen. Let me just reduce it a little. Okay, so first, click on statistics, then click on multivariate exploratory technique, and then click factor analyses. Then this dialog box comes out. The next thing that you need to do is to enter the variables that you have, that you want to or enter the items where you want to extract. Okay, by the way, the point that we're doing this one is that I wanted to determine how many factors I can have for my 30 items. So I enter item 1 until the last item, which is item 30. I just have to select them. After you select them, you click OK. You just maintain this one raw data and then click OK. Now, it's asking me the maximum number of factors that I want to extract. Let's say I want to extract about 4. Let me just put here 4. And my maximum eigenvalue that I want to see is 1.0. Right? And then you click OK. Then this one comes out. Actually, you can already see the eigenvalues here for the 4 factors extracted on top. Okay. Now, first, let's take a look at the eigenvalues. You just click on eigenvalues. Okay. Now, if I extract 4 factors, this is now the result. Okay. The 4th factor will have an eigenvalue of about 1.47. So this is telling us that it's okay to have 4 factors. Now, let me demonstrate this one further. Now, let me go back. Okay, I'll put here 10. Maximum number of factors. Put here 10, I click OK again, and I click eigenvalues again. So you will notice that it didn't proceed until 10. It stopped the extraction at 6, meaning to say the 7th factor has an eigenvalue of less than 1.0. That's why it stopped the extraction on the 6th factor. Okay, next. How do we now know what are those items belonging to each of the factors? So click here again. Okay, and then click now loadings. Okay, and then remember our cutoff 0.3 or 0.4. Let's say that my cutoff is 0.4. So you just change this one to 0.4 and then click on summary factor loadings. All right, so this is now the summary of your factor loading. So you will notice that Statistica placed in red those factor loadings that are greater than 0.4. However, you will notice that the analysis is not so good because all of the items belonged under factor 1. And those items that belongs to factor 2 overlaps with those under factor 1. And it's only item number 16 that solely belongs to factor 2. So you only have one item under factor 2, and this is not good because you only have one indicator under that factor. And you look at factor number 3, none of the items are loading highly under factor 3. Factor 4 has item 23, but it is still being shared by factor 1. And you will notice the same pattern for the others, and there are very few items on factors 3, 4, 5, and 6 that are highly contributing to these factors. So how do we now solve that problem? Our problem is actually solved by rotating our loadings. So when you say rotating our loadings, we're now maximizing the factor loadings across and around our factors. How do we do that here? You just click on this one again. And you see this one, there's a menu. Okay, and it says here that the factors are unrotated. The previous one, the factors are unrotated, but let's now rotate. There are several approaches on how you rotate. You have the Varimax rotation, and you have the Quartimax rotation and the Equimax rotation. And we'll talk about them when I shift to the slides. Let's try Varimax rotation, and let's see what happens in the Varimax rotation. I maintain 0.40, and then you click on summary after you select Varimax rotation. Okay, you will now notice that the items are now distributed across the 6 factors after you did the varimax rotation. You will now notice that items 1 to 4 belongs to factor 1, okay, including item number 5. Item 6 and 7 belongs to item 6, okay? And you will notice also that items 9 and 10 and 11 and 12 now belongs to factor 5. So we have maximized the factor loadings across the factors. So the next step here later on is look at the item contents of items 1 to 5, then give a name for factor 1. Look at the contents of items 9 to 12 and then give a name for factor 5. That's how you usually do the approach. Okay, let me go back now to my slides. Okay, so our goal now in factor rotation is to maximize the number of factors. If you will not rotate your factors, okay, this is how mathematically it looks like. You have, let's say, for example, items A, B, C, D, and E. And let's say that the maximum number of factors that you want to extract are 2. Your x-axis is your first factor. Your y-axis is your second factor. If you will now plot the factor loadings around this coordinate, okay, you will see that items A, okay, highly loaded under factor 1, which is about 0.7 and above, and only 0.6 and below for the second factor. Same goes for B, C, D, and E. So all of the 5 items, when you did not rotate your factor loadings, all belongs under factor 1. Okay, and that's not good because you're not supporting theory. Okay, because conceptually, responsibility can have factors. So you rotate now your axis. Rotating your axis means maintain the perpendicularity of your axis. You just rotate it about 45 degrees. When you rotate now your axis to about 45 degrees without touching the points of your loadings, okay, you maximize now loadings in between factor 1 and factor 2. You will notice now that the positions of items A, B, C, and D did not change, but we rotated our axis. You will now notice that item C and item A and item B now belongs to factor 2, and item D and E now belongs to the first factor because we rotated. Now, the other approaches like orthogonal rotation allows us, by the way, the previous one is a varimax rotation. This one is an oblique rotation. In an oblique rotation, you're now allowed to adjust the perpendicularity of your axis to maximize your loadings further. All right, so this is what happens in an exploratory factor analysis. And take note that you're doing all of those analyses because you are still discovering or uncovering what factors comprise your latent variable. And these are the other analyses that you can do for the purpose of exploring your factors. Okay. Now, let's go to the second approach, confirmatory factor analyses. In the exploratory, you don't have a defined set of factors yet. And you're doing the principal components, you're doing the EFA because you want to determine what are the factors of your items if you have a measure. What if your conceptual framework is telling you, okay, that there are already a set of factors? What do? Are you going to do principal components? What if, okay, you have an achievement test? There are 50 items on math, there are 50 items on English. And then you did principal components. It will happen, I'm telling you, that some of the math items will be combined with some of the English items under 2 to 3 factors. And that's not how we want our items to be. especially if our factors of an achievement test is composed of different subject areas. So the principal component analysis is not a good way if you already have an existing set of factors, especially if you have a strong theoretical framework that is now telling us that these are the factors of your measure. So if your existing conceptual or theoretical framework has existing set of factors, all you have to do is to prove whether these set of factors are supported by your data. And now you do your analysis, the second kind of analysis, which is confirmatory factor analysis. It's called confirmatory factor analysis because your goal now here is to prove whether your existing set of hypothesized factors is actually supported by your data. Okay? That's why in the slide here, okay, you use the confirmatory factor analysis to indicate how well your data fits your hypothesized structure. Your hypothesized structure is actually telling us whether you have a 2-factor structure, you have a 3-factor structure, or a 4-factor structure. And the number of these factor structures are defined in your conceptual or theoretical framework. Okay? Usually, if you are establishing your if you're establishing a variable that you made, okay, you usually start with exploratory factor analysis because you want to uncover your set of factors. Once these set of factors are uncovered and they're meaningful, you want to confirm whether these set of factors are actually true. So you do a CFA as a follow-up to your EFA. Okay, now your CFA or confirmatory factor analysis allows you to fit a common factor model to observe data under various types of constraints. Okay, now what is a common factor model? So when you say that you have a common factor model, you have a latent factor, and you're treating your factors or your subscales as latent factors as well. And the indicators of these latent factors would be your specific items. This is a common factor model. What happens in the analyses in the CFA is that the parameters of the models are actually estimated, and there are about 4 important things that we need to look at in our estimate. First is that you wanted to estimate whether the item really belongs or contributes significantly to that factor. The second estimate is looking at whether your estimates of fit is actually supporting the model. Okay, so these are the 2 things. And of course, you look at, if it's a common factor, you look at the covariances across your latent factors. Okay, now let me show you an example. If you look at the screen now, this is an example of a common factor model. And in this common factor model, okay, I think this is a bad example. Let me go to another one. Okay, wait, let me just search for. Okay, this is a better way to illustrate it. This is a better model. Okay, look at this particular model. So a couple of years back, we constructed a scale, and the scale measures factors of giving feedback to students' essay. And there are 3 factors that we were able to extract in a preliminary exploratory factor analysis. We found out that the factors of giving feedback to an essay would be feedback on the form, feedback on the content, and feedback on the writing style. Feedback on the form would refer to the mechanics, grammar, punctuation, etc., etc. Feedback on the content is the organization of ideas, strength of the ideas, whether there are evidences to support the ideas. Feedback on the style is the writing style. Okay, so there are 3 factors that comprises feedback for writing. We call this a common factor model because if your three factors, feedback on form, feedback on content, and feedback on writing style, are really measuring the same variable, which is feedback, if they are really measuring in the same common factor, such as feedback, they should be highly correlated with each other. That's why you see that there are bent arrows that connects these three factors together. Okay? Aside from that, you will notice that there are rectangles, okay, that are pointed from the circle going out. These are the items, okay? So meaning to say, these items here on top, the rectangle items here on top, that with arrows pointed at them coming from the latent variable are the items under feedback on form. These items here, you will see item 13 to 28 here are the items under feedback on content. And the items here, items 16 to 30, are the items under feedback on the writing style. What we did here is that these items are hypothesized to be measures of feedback of form. Items 13 and to 28 are hypothesized to be under feedback on content, and items 16 to 30 are hypothesized to be under feedback on writing style. We wanted to prove whether this set of items really belongs to the respective latent factor. Latent factors are the ones on the circles, and they're called latent factors because we do not directly measure them. In order to measure latent factors, you need to have the items, or what we call as manifest variables, because the manifest variables are the ones that are directly measured, which is your items in this particular case. Okay. You will now notice that there are numbers on the arrow. These numbers are what you call as parameter estimates. Okay? So you now look at the parameter estimate to say whether that item really belongs to that latent factor. Okay? So how will you now know later on whether these set of items belongs to feedback on form? You will check later on whether these parameter estimates are significant or not. If they are significant, it means to say that they belong to that latent factor. If they're not significantly explaining the total variance of that latent factor. Okay? And usually you can drop off later on these items that are not significant. That's the first estimate that you assess. The second estimate that you assess is the goodness of fit of the entire model. So take note that this is called a three-factor model because it is composed of three factors: feedback on form, feedback on content, and feedback on writing style. And this is a common factor model because feedback on form, feedback on content, and feedback on writing style are the factors of feedback to writing. That's why it is a common factor model. They're measuring a common trait or variable. Now, the other estimate that we look at and assess here is the goodness of fit. So when you say goodness of fit, whether your data is supporting this set of factors, okay? And you will notice that here on the side, it says here, the goodness of fit indices obtained were, and then you have a chi-square, okay, expanded to a matrix algebra, is an estimate of goodness of fit, and it should not be significant. If your chi-square is not significant, it means to say that your three-factor solution has goodness of fit. Another one is the root mean square residual, and you need to have a very, very small root mean square because your root mean square residual is an estimate of error. And usually your cutoff here is about 0.8 and below. If you have 0.8 and below, 0.08 and below, it means to say that you have a goodness of fit. The solution fits your three-factor model. Same thing with your goodness of fit index, GFI. You need to have at least about 0.95 and above, including your cumulative fit index or CFA. At least you need to have a 0.90 and above. So you will notice that your GFI is 0.96 and your CFA is 0.92. meaning to say that your data is supporting well the three-factor model. And you also have your RMSEA here, root mean square error approximation. This is again an estimate of error, which is 0.08, and it's telling us that, okay, your data, which is about, I think I have 1,400 participants here, that data is supporting this particular model. Okay, so that's the second estimate, the goodness of fit estimate that you need to look at. Third estimate, you will notice that there are bent arrows that connects your latent factors. And on the bent arrows, there are numbers like 0.11 here between feedback on form and feedback on content. 0.19 between feedback on consent and on content and feedback on writing style. And 0.14 between feedback on form and feedback on writing style. This is actually correlating your latent factors. Okay, these are actually covariances. And the covariances among your latent factors, if they are significant, will now tell you whether you have a common factor model. I think in the analysis, all of these three covariances are significant. So we can say now that these three factors are common factors to feedback on writing. All right, let me go back to my previous slide, and let's talk a little bit more on the goodness of fit. So take note again that goodness of fit is telling us whether our data is supporting our solution or the number of factors that we have. And we have two approaches of looking at goodness of fit. You have the non-centrality interval estimation and the single sample fit indices. All right, so first, the non-centrality. Non-centrality indices are error estimates. It tells you how much error is your data in supporting your model. Okay, the first estimate, you have the Steiger-Lind RMSEA. RMSEA stands for root mean square error approximation. Okay, so this is actually an estimate of error. That's why you want this error to be small. Okay, at least about 0.08 and below. If you get a value of 0.08 and below, then it means to say that your data supports your model. Another one, you have the McDonald's index of non-centrality. At least you need to have a value of 0.95 and above. If you have a value of 0.95 and above, your data supports your model. The next one, you have the PGI, or the population gamma index. At least again, you need to have a value of 0.95 and above. Then you have the adjusted population gamma index, or the AGFI. So same thing, you need to have 0.95 and above. Other estimates, you have the Joris-Cog GFI and the adjusted Joris-Cog GFI. You have an adjusted value for every estimate, especially they derive an adjustment measure, especially if your distribution is not normal. So you need to have the adjusted value considering if the data that you have is non-normal, especially if you have few observations. So if you get a value of 0.95 and above, then your data is supporting your model well. Now, you also have the comparative fit indices. Okay, examples of comparative fit indices would be your Kaiser information criterion, your Schwarz-Bayesian criterion, and your Brown-Kudek cross-validation index. You use these three when you have more than one model, and you are comparing which among the models is the best fitting. Okay, and usually the smallest value for the Brown-Kudek, for the Kaiser information criterion, and for the Schwarz-Bayesian criterion tells you that that is the model that best explains your data that best explains your model. Okay, let me give you an example here. Okay, let me use another one. Okay, here. In a previous study that I did, because I'm looking at the construct validity of a scale that I made, which measures self-regulation. Self-regulation measures a variety of learning strategies. similar to other existing scales, such as the MSLQ and the LASI. MSLQ is the Motivated Strategies for Learning Questionnaire. The LASI is the Learning Attitude Strategies Inventory. Okay. Now, I selected the MSLQ and the LASI because the items are indicative of learning strategies as well. So meaning to say, if the correlation or the covariances of MSLQ and LASI are significant to the self-regulation measure that I made, then I can explain, then it means to say that my self-regulation is a valid measure because it's measuring the same content. They're parallel. All right. So you will notice that these are my factors under the self-regulation. You have memory, strategy, goal setting, self-evaluation, etc., etc. Here are my factors for the MSLQ. You have values, expectations, effective, etc., etc. You have the LASI. Okay, and here are the measures of the LASI. So in my model 1, I separated the 3 as separate latent factors, each having their own factor, and I intercorrelated them through the bent arrows. In the second model, okay, on the left side of your screen, I combined my measure of self-regulation with the factors of the MSLQ on a single latent construct. So you will notice here, the rectangles are all combined factors of the self-regulation of the MSLQ. And I separated the LASI. I wanted to test in this particular model whether this model where I combined self-regulation with the MSLQ and separate LASI would be better as compared to my previous 3-factor model. Now look at my third model on the right side. In the third model this time, I placed together the self-regulation and the LASI measure this time. So I placed all of their factors under one latent variable, and this time what I separated was the MSLQ. I'm trying to test here whether self-regulation is more compatible or more similar with the LASI versus MSLQ as a separate latent factor. Okay, and I wanted to compare this model versus the first 2-factor model and versus the original 3-factor model. So I'm testing 3 factors here. So my aim here is to determine which of my 3 models would best explain academic self-regulation. Is it when it is combined with LASI? Is it when it is combined with the MSLQ, or when it is separate with the LASI or MSLQ? So therefore, I computed for my comparative fit index here. Here are my comparative fit indices. So you'll notice here in the first column are my fit indices. I have here my chi-square with the corresponding degrees of freedom, my root mean square, error approximation, RMSEA, okay, standardized, root mean square residual, and I have the last 3 estimates, AIC, Akaike Information Criterion, SPC, Schwartz Bayesian Criterion, and the BCCVI, Brown-Kudik Cross-Validation Index. So the second column here is my 2-factor model where I combine self-regulation with the MSLQ. Second model here is the third column where I combine self-regulation with the LASI, and the 3-factor model where the 3 variables are exclusive. You will notice that in the AIC, SBC, BCCVI values that the lowest values are all under the 3-factor model. So meaning to say my data is supporting a 3-factor model, meaning to say self-regulation has some unique content that can be distinguished with the LASI and the MSLQ. That's why a 3-factor model is supported. Okay, let's go back to the other estimates. Other estimates of goodness of fit would be, of course, your NFI or your norm fit index. This is useful, especially when your distribution is not normal. Same goes for the Bentler-Bonet norm fit index and the Bentler comparative fit index. So the Bentler comparative fit index is also used to compare several models. However, this is based on a goodness of fit. The AIC, the BCCVI, and the SBC are derivations from your chi-square estimate, but the Bentler CFI is based on the norm fit index that was derived by Peter Bentler. So Peter Bentler is my professor in my PhD when I took my doctorate. Okay, so these are the other goodness of fit estimates: James Mulake, parsimonious fit index, Bolen's Rho, and Bolen's delta. Now, there are several goodness of fit. Do you need to use all of them? Anderson and Gerbing said that at least there are 3 goodness of fit estimates that are telling you that your model is fitting well, then that's enough. Okay, so this is how you actually report and interpret the results of a CFA. Okay, so you can say, for example, that the results show that the 3-factor model is best fitting model, indicating further support for the emergence of self-regulation with the Emerson-Lassie, and then you put in parentheses the values of regular fit. What is common in all 3 models is that there are significant paths. All right, let me. I think there are some in the chat box. Okay.
Yes po, Doc. There are a few questions po.
Okay, good morning, ma'am. My question is possible to after a continuous exploratory factor. Okay, later on we'll just look at the question. Okay, let me just go and demonstrate how we do this one, making use of a software. Okay, you can see my screen now. You can see my statistical screen.
Yes po, Doc.
All right. I'm just closing them. Do you want to? No. Save changes? No. Okay. First, let me start with my Excel file. So let's work out on the same data set, which is on responsibility for learning. So responsibility for learning was actually made by Benvenuti and Kit Santas. They're my colleagues from the City University of New York. I was visiting Prof in CUNY from 2012 to 2014, and I was co-teaching on a course on self-regulation with Dr. Benvenuti. All right, so the concept on responsibility for learning in the framework is composed of 3 factors. You have deportment, okay, and I made 10 items that measures deportment. The second factor would be learning process, and there's another 10 items on the learning process. And the last factor is motivation. So meaning to say I already have a theoretical framework for responsibility for learning, and theoretical framework says that it's already composed of 3 factors. So I don't have to reinvent it again if I wanted to use it on a particular study. So let's say that the purpose of my study is to confirm whether these 3 factors are supported by my data. Okay, so you will notice that in every row you have a participant, and in every column you have the items. So in order for this one to be analyzed in the CFA inside Statistica, you need to make a covariance matrix first. Okay, so how do you do that? Okay, in Excel. Okay, I hate it in Zoom when the menu comes out because, all right, so here. So just click on data. Okay, you have to install first. Okay, I have a new Microsoft Office pala. You have to install first the VBA toolkit, okay, in your Excel. So click more, click options, click add in. Okay, and then after you click on add in, click on analysis VBA toolkit. Okay, and that's an analysis. Yeah, that's an Excel add in, and then click go. And then check here, analysis toolpack VBA. The 2 of them, click OK. So it's now installing my analysis toolpack. Now you will notice that suddenly a new menu appeared here on top because I already installed the add-in. So click on data analysis here. Okay, click on covariances. Take note, we're doing this one because we want to create a covariance matrix out of my 30 items. Click on covariance, click on OK, And then this time we'll have to input the range. So we start with item 1, D1, deportment, select until item 30, and then select all of your data here. So I think I have about 2,053 data sets. And then click on that the labels are in the first row because you've included them, and then click OK. Okay, and then this time, this is now your covariance matrix. Now, below your last item here in column A, you have to put additional syntax so that Statistica will know what to do with it. So first, you have to tell Statistica that it needs to estimate the means. Second, you have to put std.dev because you're telling Statistica that it has to estimate its own standard deviation. Then you type here cases. So I have 2,053 participants and put the 2053 other column B beside cases. And then you type the word matrix, okay, in column A below cases, and then you put 4. Matrix 4, you're telling Statistica that the values here are covariances. All right, I'll save this one. Okay, let me name my sheet. Let's say I named my sheet Cov2, covariance 2. I'll save. Okay, I will now close my Excel file. I'll go back to my Statistica. I will now open that covariance matrix that I've created from my Excel inside Statistica. I'll open, and yeah, I have to search for the file where I placed it again. Ito na nga lang. Okay, here. So again, you click on all files so that all files will appear. I placed it inside the lower version file. So I'll only import selected, and I named it Cov2, that sheet. So I'll select Cov2, I click OK. This time, make sure you put a check, get variable names first row, put a check, get variables names first row and first column, and then click OK. You will notice that the labels on the first column were integrated on the tab here and here. And you will notice, you see your labels, mean, standard deviation, cases, and matrix. They're all integrated on the first column tab, and the only values that comes out are the quantitative values. Okay, you're now ready to do your CFA. Click Statistica, click Advanced Linear, Nonlinear Models. Click, okay. Okay, click Advanced Linear, Nonlinear Models, and then click Structural Equations Modeling. Click your path wizard. Make sure that the radio button is clicked on Confirmatory Factor Analyses. Click OK. Okay, now in the tab here, it's asking you now what is the latent variable that you want to use. Okay, let me name my first latent variable, which is deportment. Let's say I will name it DEP, and then I click the variable beside it. I have to now put in my hypothesized variable under deportment, and I labeled them already, which is items 1 to 10. Click OK. My second hypothesized latent factor would be the learning process. Let's say I will name it that one, learn P. Click on variables, and my learning process, I'll put it under, that's actually item number 11 until item number 20, and then click OK. And my third would be motivation. Let's say I'll name my latent variable MOT, click on variables, and then I do the same thing. I enter my latent factors under that one, and then I click on OK. Now, because I wanted to estimate relationships across my 3 latent factors, I want to see the covariances because they're a common factor model. Make sure to click on factors here and then correlated. And then let's now do the estimation. You click OK. Okay. First, select everything and then correlate everything. Okay, so the syntax here is now telling us that learning process is going to be correlated with deportment. Motivation is going to be correlated with deportment, and motivation is going to be correlated with the learning process. Okay, and then click OK. And then yes, let's append now the syntax. Click OK. Now, you will notice here that the latent variables in the syntax are enclosed in a parenthesis, and your manifest variables are enclosed on braces. And you will see these syntax where there is a greater than sign. If there's a greater than sign, it means to say that we're estimating that these manifest variables are under that latent variable. Same goes for the learning process, same goes for the motivation. You will also notice that there's delta. So what are these deltas here? The deltas is the syntax in Statistica indicating that we are also estimating standard errors for every manifest variable. And then look at the end. This is now your syntax for intercorrelating your 3 latent factors. Okay, let's now run the model. It's now going through an iteration. It will stop until it reaches 0. And then you click OK. Now you're ready to view your model. So click on your model summary. Okay. Now, your model summary here is telling you that the parameter estimates of item 1 to item 10 are significant. Take a look at the probability levels here. This is your p-values. Since they are less than 0.05, they are significant. It means to say that these 10 items significantly contributes to deportment. Same goes for item 11 to item 20. Okay, they all significantly contribute under the learning process. And items 21 to item 30 are significant items under motivation. Okay, so I was successfully able to prove that my 10 items really measures those 3 factors respectively. And then look at the last 3 rows here. The covariances between learning process and deportment, which is 0.80, is significant. Same thing, covariance between motivation and deportment is significant, and the covariance between motivation and the learning process is significant. So first step, look at your estimates. Second, let's now estimate the goodness of fit. Just pull out that menu again, and then click on basic summary statistics. Okay, it's telling you that your chi-square is 4701, and it's significant. So chi-square is telling you it's a bad fit. However, chi-square is very sensitive to large sample size. That's why chi-square is not usually used as a good measure for fit. So you use the other ones. So look at my root mean square standardized residual. It's 0.05. It's telling me that my data has few error variances. Let's look at the other fit indices. Pull out this menu again and click on advanced. And then click on non-centrality-based indices. So look at now my point estimates. My RMSEA is 0.08, so quite good fit. Look at my population gamma index 0.85, so it's telling me it's a bad fit. Also my adjusted population gamma index. However, my RMSEA is quite okay, it's 0.08. Let's take a look at other goodness of fit indices. Click this one again and click on other single sample indices. So you will notice that GFI is 0.84. Okay, adjusted one is 0.81, and then the others are about 0.7, so it's a bad fit. So we have to make some adjustments in my data so that my data is going to fit, and I need another day to explain how to fit a bad fitting model. All right, so this is how we do the confirmatory factor analysis. I like doing confirmatory factor analysis because especially if you begin your study with already an established set of variables rather than reinventing the framework from the beginning, because the reviewers will tend to ask several questions. Okay, and then ultimately it's going to be rejected. That's why sometimes it's wiser to use already an existing model, and all you have to do is to say whether your data is supporting the factor solution that you have. Okay, let's now take a look at the questions. Okay, so there's a question here. Okay, what do negative factor loadings trying to imply? Okay, not much really. It's just reversed. Okay, as long as even if the factor loadings are negative, as long as it's 0.3 or 0.4 and above, it means to say that the item is highly loading. How will we choose the best factor rotation in our data? Good question. Try all. Try oblique, try varimax, okay? Try quartimax. whichever is the best solution that will explain well the classification of your items, go for that one. Okay, if you have a 10-item questionnaire, what is the minimum sample size to make the PCA? Okay, now if you use a traditional principal components analysis, according to authors like Develis, he said that you need to have a sample size of about 2.5 times the number of items. So if you have 10 items, at least you need to have 25. However, take note, 10 items is not good when you do principal components. Take note, you want to reduce the number of factors. And 10 items is so few. What if eigenvalue would be 9? So it's useless. So usually you go for about more than 50 or more items. Okay. How many latent factors of feedback on writing at the start? 3. So we began with 3. We derived that through the original model on giving feedback by Hattie and Timperlake. Okay, and then we contextualize our own by Saturnino. Jerwin, what if one of the following RMR, GFI, CFA, RMSI does not meet the minimum? Are we allowed to proceed? Remember what Anderson and Gerbing said. Look at all other fit indices. As long as you have 3 fit indices that supports your model, that's going to be fine. And just report in your study those 3 that supports your model. Now, your problem is, what if all are not, what if all of your goodness of fit estimates indicates that they're not supporting your model? Then you make adjustments in your model. How do you make adjustments in your model? 1, drop those items or variables that are not significant. Drop those manifest variables that are not significant. 2, if when you start dropping those non-significant manifest variables and you're left with very, very few manifest variables for a latent variable, try to combine it with the other latent variables and try to generate again the fit and try to see if there's improvement. Another approach is to correlate the standard error of estimates. If you correlate the standard errors of estimates within the same latent variables, it usually improves the goodness of fit. Okay? Yes, so these are some of the techniques. The others, what they do is that they go back to the raw data. They take out outliers. Okay, how do you take out the outliers? Well, you estimate you estimate which ones are far away from your regression line, such as using the Cook's distance and the Mahalanobis distance estimates. They will tell you that if you have very, very large values for that particular respondent, you can take out that respondent. Try taking out those respondents who are outliers, and then run again your analysis, try to see if the data would fit. Okay, another. Wow, I'm so excited on comparison of 2 or more models, sir. Can you share an example of researches? I think I've shared examples of 2 or more having 2 or more models. And then according to this set, I appreciate the visit, but I am a bit lost na po. Huge background on stats, technical po. All right, probably next. If you have questions and which part are you lost, you can actually specify here. Okay. Your teacher is Dr. Ibe. Yes. Okay, Keith. Good morning, Dr. Magno. My question is it possible that after conducting exploratory factor analysis, a researcher can also conduct multiple regression to determine whether the derived factors are predictors of a certain outcome? Yeah, this is also possible. But take note that your statistics are sourced and selected based on your research question. If your first research question specifies how many factors, then do CFA. If your second research question is now saying whether the factors extracted significantly predicts an outcome, then you follow it up with multiple regression. So again, take note that your statistics is dependent on your research problem or your research question. So my possible study is exploring the factor structure of mastery in general mathematics. May factor structure ba ang mastery ng mathematics? Meron na tayong factors ng mathematics, sir. Keith, okay? In our curriculum, we already have factors of mathematics, number sets, patterns and algebra, measurement, statistics and probability, geometry. So hindi mo na kailangang i-uncover ang factor structure ng mathematics curriculum dahil meron na po, Sir Kit. Ha? Okay. You don't have to do principal component. It's a bad idea to do exploratory factor analysis for subject area domains like mathematics and English because they are already defined in the curriculum. It's best to use confirmatory for these variables. Elaine, Hubo, is Statistica software downloadable or not? No, you have to buy Statistica, but there are freewares where you can do exploratory and confirmatory factor analysis like your JASP. I'll send in a while the link where you can do it in JASP. Saturnino, can we be given a cracked version of Statistica? Yes, I have a cracked version of Statistica, but you'll have to send me your flash drive so that I can, save it in your flash drive. Will we be given Statistica installer if not CFA? Okay, probably I can give, the organizer can send me a flash drive. I'll put it there, and then it's the organizers that will send out the files to you because I can't put it inside the drive. The drive is not accepting the file. It's too big.
Okay po, Doctor.
Okay,
Thank you
Lisette
po.
Carus. Is there a trial version of Statistica? I am downloading it now. There is. Okay, sige, good. If you use the trial version. Jerwin, thank you, sir. Lisette, ma'am, for how long is the trial version available? Okay, from JR Dubli, sir, how SEM model and hierarchical regression analysis related? Okay. Structural equations modeling and hierarchical regression have some similarities. Okay, both of them can estimate variances, okay, in terms of the relationship among your factors. However, your hierarchical regression, okay, only works when your variables are all manifest. Okay, you cannot use latent variables for hierarchical regression. But in SEM, you can work out with latent variables comprised of manifest variables that are observable. Nada-download po ba yung sinasabi niyong sample research ng 2 or more models compare? Yes, Saturnino, you can actually type my name in Google. Okay, Dr. Carlo Magno, and then one of the links will come out. I have a Google site, and then you click on one of the menu publications, and then there are several studies there where I did CFA and compared several models. Saturnino, you can check it out. Okay, let me put the link here, Saturnino, on the chat box so that you can see where you can get examples. You just get from one or choose from. Okay, let me put it in the chat box, everyone. Okay, so there's the site now. Also, I'm going to give you the link for the JASP so that you can practice doing CFA and EFA. So JASP is freeware and you can do all of these analyses. Okay, also the one that gives you free and you can do all kinds of analyses would be R. However, in R, you have to type on the syntax. Okay, so that's the link where you can actually download the JASP. Asa na tayo? How long is the trial version? How is the hierarchical? Okay, ma-download po ba yung sinasabi mo na sample research? Ito na. Is probability sampling essential for collecting data for Explorer? Okay, this is a good question, Jerwin. The answer is like this. if you're not generalizing if the purpose of your study is not generalizing for a larger population, okay, you don't need to do random sampling. But if what you're after in your study is generalizability in terms of the theory, okay, then you don't need to have random sampling. The requirement in doing confirmatory factor analysis is a large sample size, at least about 320. There are cases that if you have very, very few observations, like 100 or less, CFA will not run. The iteration will stop. Okay? That's why at least it's safe to do a sample size of 320 for doing CFA. Okay, where can we find a literature factor structure of the subjects? Okay, saan daw ang literature review ng factor structure ng subject? Well, practically, the curriculum guide points you already to the factor structure, yung mga components from your curriculum guide, Ivan. Okay, yeah. So, yeah, other questions. You can actually unmute or you can type on the chat box if you have other questions. You still have about 7 minutes. Go ahead. Okay, any other question? Okay, if there are no more questions, okay. So thank you very much, everybody.
Thank you so much, Dr. Magno. Maraming salamat po. Information overload kami ngayon sa
Yeah, you need
factor analysis.
several days to study just one form of analysis.
Yes po. Thank you, Dr. Magno. May I just request for a picture
Okay, wait,
taking
let me
po?
just upload the slides because they're requesting.
Yes po, Doc. Even last time po.
Okay, I'll just put it in the
PDF.
link. Okay, give me 1 minute. PQR.
Dear participants, I'll be the one to download na lang po. Then, upload ko po sa Google Drive natin. Okay? Paki-check na lang po doon.
Okay. It's being uploaded now. Also the one for content, for validity. Okay, it's uploaded. It's there now in the chat box.
Thank you po, Doctor. Okay po, picture taking po. Ready? Thank you po, Doc. 1, 2, 3. First frame. Next. Second frame. Third frame. Fourth frame. Fifth frame. And last frame. Okay po. Maraming salamat po, Doc. Maraming salamat
Okay,
po.
sir, I need 8 advanced volunteers for tomorrow who will
Okay
recite.
po. Sige po, Doc. Post ko po before we start tomorrow.
Okay. Bye-bye, everybody.
Thank you po. Thank you, Doctor.
Enjoy the
Maraming
rest.
salamat.
Yeah, enjoy the rest of your weekend.
Thank you, everyone. Have a good lunch po. Thank you po.